You have stuff for me, please. I did talk about the ordering a little bit last time. I want to make a couple more specific statements. These are all in the text on page 288. Sorry, 228. If I have numbers bigger than 1, B bigger than C, then the smaller one is dominated by the bigger one. The smaller power is dominated by the bigger power. And this is not symmetric. But those only work for positive powers bigger than 1. If I'm dealing with powers that are smaller than 1, we have some issues. Talk about that more in a bit. If I'm dealing with any two positive numbers, though, any logarithm in any base can be dominated by any polynomial. No matter what the power is there, as long as it's not negative. And really, what this means to me is that any logarithm power is in big O of n to the first. No matter what power of logarithm you are looking at, it is always dominated by just big O of n. If I have a base B, like I was using a base here, any power is dominated by an exponential, as long as the base of that exponential is bigger than 1. But not the reverse. Every power, no matter what, 10 to the n to the 100th, is still dominated by 2 to the n, eventually. And nope, that's wrong. C to the n is in D to the n. I used B and C. Why am I using C and D? Scratch. Let's try this again. B to the n is in C to the n. So 2 to the n is dominated by 3 to the n. 3 to the n is dominated by 4 to the n. Bigger number base dominates. This is a convenient shorthand when it comes to me figuring out what's the overall big O of a particular expression. I'm really only going to look at which one of these is the top. But a lot of expressions are built from lots of different pieces. So what happens if I'm combining more than one function? If I have two different functions, f1 and f2, and I know the order of those, then I know the order of their sum. It isn't G1 plus G2. Darn, that would have been so easy, wouldn't it? It isn't. It's whichever of those two is bigger. It doesn't actually matter. If one of those is an x squared and the other is an x cubed, it's not big O of x squared plus x cubed because the x cubed beats the x squared. That's what this statement said up here. So I really only need the biggest piece whenever I'm adding. By the way, this means if you add two things that are of the same order, the order doesn't change. So adding doesn't actually change order. If you think about the witnesses for the bigger function, the witnesses for the bigger function work for the smaller function. What does change is multiplying. Now, this is particularly useful to me because a lot of the expressions I'm going to work with are going to combine functions like this. Now, the question I am looking at asks me to find n, so f is in big O of x to the n. Huh. This is power of a logarithm, right? If that's my f2, what's the order of this? In terms of a power of x. We just wrote it down. Colin? Exactly. Every logarithm, no matter what the power is raised to, no matter what the base is, this piece is big O of x to the first. What about the other piece? That's polynomial. And we said polynomials are big O of? This was Friday. Big O of the highest power involved. And in this case, that's x cubed. So this piece is in big O of x cubed. This piece is in big O of x. I'm adding those. So that means we are in the big O of x cubed, whichever one is bigger, x cubed. So that means when x is a large number, the graph of this looks like a cubic equation if I zoom out far enough. That log stuff really doesn't make a difference in the long run. It's too small to matter. Our generalizations work for negative powers of x also. So in spite of the fact that I'm writing this as division, I'm going to think of this still as multiplication. Think about the function on the top. What big O is that? In the same setup as we used previously, that's x to the fifth. Because the logarithm is so small, it doesn't matter. If I go through what I did here, I get exactly the same thing. The top is big O of x to the fifth. And similarly, the bottom. Because in the long run, that plus 2 doesn't really make a difference. But I'm thinking of this like this. And if I do it this way, then I agree with you that this part is big O of x to the fifth. But what about this part? Because it's in the bottom now, that's big O of x to the negative fourth. That's sneaky. But these are being multiplied. So what does that tell me about f? It's just x to the 1. I multiply these two together. Questions? Go back to Friday's notes again. What was our definition for big O? The f of x is big O of x in that order. I'm not sure that was our original definition. Something about witnesses. Does that help? There are these two numbers, C and K, so that what? Well,
Stop there is AC and K with the absolute value of f of x is equal to C multiplied by the absolute value of g of x. X is greater than K.
so big O notation is an upper limit. It says as we go off to infinity, you are less than some multiple of, like in this case, you're less than x, some multiple of x. It might be 1x, it might be 5x, it might be 73x. I don't know. It might be 0.3x, but you're still bounded above by a straight line. Your function is down here. If I turn that inequality around, I'm looking at a lower bound for my function, right? I'm trying to say, oh, my function is going to live above this thing. I can do this same idea if I just switch that inequality. This is a lower bound. Now, you'll see very few people use this specific idea, because you'll notice if I have f is less than or equal to c times g, this sentence right here is the same as 1 over c times the absolute value of f is bigger than or equal to the absolute value of g. Yes? And isn't this saying that g is in less than or equal to f? So this big omega idea, a lower bound, is really switching g and f. F is in big omega of g if and only if g is in big O of f. So a lot of time people will really only use big O. But what they're really trying to say is that we have an upper bound, and if you switch the two around, we have a lower bound. That's actually a useful idea, because sometimes I want to know that we have both. So a way to combine these is to use a theta. I have never, ever, ever, outside of this textbook, run into somebody who uses this notation. But this actually means that I have a multiple of g below my function and another multiple of g above my function. Oh boy. I picked one that was weird on purpose. We haven't talked about trig functions at all, have we? Wow. I get to go all the way back to my trig course. I'm going to pick whichever of the big O's of this is larger, right? What is the biggest cosine can give you? Adam? 1. And if it's less than or equal to 1, then for any x bigger than 1, it's less than or equal to x, isn't it? This number is less than or equal to 1. That means it's big O of 1. The other part is big O of x, right? So this whole thing is big O of x, isn't it? But if I actually graph this, it's going to look like that, isn't it? That's x plus cosine of x. It keeps going, but it wiggles, right? Couldn't you put a line above this and a line below it? And it would be always between those two lines? Not 9x, 0.9. X, 1.1. X. It's always less than the point, bigger than 0.9x. It's always smaller than the 1.1. That's big O of x. And it's big theta of x, isn't it? It's bounded below by a multiple of x and above by a multiple of x. That's big theta of x. It's stuck between them. And that means really in the long run, the wiggles caused by that cosine are irrelevant. This behaves like the straight line y equals x. As you go that way, it goes up. A lot of computer science journals use big O when they mean big theta. We talk about these as F and G being the same order. And this is a symmetric result. F is of the same order. That means that X is the same order as F. In this case, it's reciprocal. By the way, this is related in calculus to L'Hopital's rule. If you think about what I'm doing is I'm taking the limit as x goes to infinity of these two functions when I'm comparing them. And to say that f is dominated by g, f is big O of g, means that f over g should have a limit that goes to 0. To say that f is the same order as g means we should have a limit that isn't 0 and isn't infinity. And to say that f is big omega of g means that limit should be infinity. If you haven't gotten to L'Hopital's rule yet, don't panic. We'll get there. Questions? So what the does this have to do with algorithms? Okay. The general idea here is one called computational complexity. And it really has two trade-offs. There are two different ways I can think about how good my algorithm is at doing the things I want it to do. I can ask if I know the size of the input. I can ask two different things. How many steps? How long will this take to complete? We don't actually measure this in time, but we think about it in time because each step takes a certain amount of time. The reason we don't measure it in time is because computers get faster and faster and faster all as long. As we keep going, the computer is going to be faster and faster and faster. The very first computer I owned had a processor speed in the kilohertz range, thousands of applications per second. Your MacBooks operate at 2.2 gigahertz, billions of operations per second. You are literally a million times faster than my old Commodore 64. And the computer I used before that ran on a tape drive. Yes, reel-to-reel tapes. The other thing I can ask is how much memory does it take to do this job? So if we think of the first one as how long is it, then the second one is how big is it? Now, this again was a very large problem. Computers did not have a lot of RAM to them. The very first electronic numerical integrator and calculator had a memory of 100 bytes. Sorry, 128 if I'm being precise, but 28 of them were taken up by the system instructions. Literally, each one was a physical tube which stored either a high signal or a low signal, a bit, by sending current through one wire or the other, by flipping a little bit of an electromagnet inside. That's a transistor. A transistor tube, by the way, this is why you have to let your electronics warm up, because the tubes only worked once they got warm enough, which meant in the middle of winter, you'd turn your television on and wait 5 minutes before the picture showed up. By the way, this is also the origin of the word bug for computer bugs. I've forgotten her name. She's a colonel. Grace Hopper, Admiral Grace Hopper. Grace Hopper was the programmer for ENIAC. And she came in one day and it wasn't working. And it turned out a moth had been attracted to the glowing light of the tube and had whacked itself into the tube so much that the tube came unseated. By the way, the bug died because of how hot the tube was. Moth to a flame, right? So it was stuck on the side of the tube. She went in, peeled the bug off, reset the tube, and taped the bug in her logbook. The very first computer bug. I wish I was making this. World is crazier than I can imagine. So, I can think about time complexity and space complexity. The more memory I have, the more I can just say, well, leave that over there. I'll get back to it when I need it. And then it's in memory, not on a disk where I have to go access the disk. It's not in a book somewhere. It's in my head. I don't have to go look this up. I know it. That's faster, isn't it? So I just kept everything in memory all the time. I'd not have to worry about how long it took me to get stuff. This is why books were invented, so I could offload some of that crap. At some point, the physical limitations of how big an algorithm is, how much memory I've got, come into play. So you've got huge amounts of memory. It is still possible to crash your machine. There is also the issue of the physicality of computers. A computer chip is a physical piece of silicon. And instead of having a tube for a transistor, we have two little layers of silicon with some metal in between them. And we allow the electromagnetic properties of the chemicals to replace the electromagnet that was in the tube. And you can make those smaller and smaller and smaller and smaller. It's called VLSI, very large scale integration. And the smaller you make these items, the more of them you put on a computer chip. And that's why something the size of your thumb can hold 4 gig, right? Or 16 or 64, because we made the processors smaller and smaller and smaller. At some point that breaks because of quantum behavior. And the electrons don't go down the wires, they kind of jump all over the place. The wires get too thin. We're almost there right now. We're not truly there, but we're almost there right now. So I want to think most of the time about the trade-off between these two. I can run faster by using more space. I can run longer if I use less space, and it'll be more efficient. How much money do I have to spend on space? How much money do I have to spend on processing time? They're two different trade-offs. Let's go back and think about time measurements. Let's use my linear search. We wrote down the algorithm last week, right? Let me go grab my algorithm. Here we go. Here's my linear search. I'm looking for the number X along the list A1 through AN. The only thing I know about those is that they're all different. This says start your counter at 1. While your counter is less than or equal to N and X is not equal to AI. Keep going. And then up the counter. I asked for the number of comparisons we are doing. What are we comparing? Well, we're comparing I to N, and we're comparing X to AI. So that's 2 comparisons right there. But those are in the loop. What is the maximum number of times I will do those 2 comparisons? N. Because I got to go until this condition hits or this condition hits. If the number's not in my list, I'm going to go through the whole list, aren't I? So there are 2 N comparisons right there. By the way, then we drop out of the loop. We do 1 more comparison, and then make a definition based on that, right? So I did 2N plus 1 comparisons. And now I can say with absolute certainty, this algorithm has a complexity level. It is going to take 2N plus 1 steps for a list of length N, right? There are also some other things that happen here, right? I have to also take into account that I am adding one to each of the counters, right? Let me put that n back up here. Additional steps. I have to increment the count. Somewhere in the back of this computer's memory is something going 1, click, 2, click, 3, click, 4, click, 5, right? It's got to keep track of where we are. Those are steps. Typically, these are referred to as bookkeeping steps because they're not actually doing the work, they're keeping track. There's also one more step being done. I'm assigning location in my very last step. So once I've dropped out of the loop, I do this comparison. That was the +1 in the comparisons. And then either location gets defined there or there. So there's one more definition, right? Spit out, and then one command, spit out location. So there are really 2 additional steps for the outputs. But that's going to happen regardless of how many things I have in my list, right? They're not going to matter to the size of the list. Now, this is an additional n steps. These are 2 more steps. Technically, if I count all the steps, I've got 3n plus 3, right? But here's the best part. That is big theta of n. That's bounded below by 3n, is bounded above by 4n, whenever n is bigger than 3. Here's the C for the big O, the 4. Here's the K. Here's the C for the big omega, 3. Going with the same K. This algorithm really just depends on how much stuff you're giving me in the list, right? In terms of the number of steps, the time complexity of this algorithm, I'm going to say, oh, this is running in n time. Most computer scientists will not use theta. They will simply use O. Regardless of the fact that they really mean theta. They'll talk about this as an upper estimate only, not really caring about the bottom estimate. This is the heart of algorithmic complexity, trying to figure out how much time we need to run our algorithm. I did not talk about space at all here, did I? So let me think about the space for a minute. How much space do I need to do this? I need to store the location of I. I need to store all the numbers of my list, so that's n. I need to store x. So right now that's n plus 2. I need to store something location when I'm done, so that's a 3rd spot. The only other thing I need to be able to do is to make the comparisons. Here to here, here to here, here to here, here to here, right? Between x and each item in my list. That's another yes or no that I'll have to store as a Boolean value somewhere. So far I have X, I, location, comparison, result, true or false. And then my N. That's also big O of N, isn't it? Because it's N plus 4. There's a trade-off here. I could make more space. I could write down instead of all of the individuals, I could make this take much less time. If I just said, here's every possible pair, AI and X. Do any of them match? Isn't that basically doing the same thing? One for A1X, A2X, A3X, A4X. Did I write the same thing once? Stop. This is usually referred to as worst case analysis. We're looking at the longest it's going to take something to get done. If I can do this in time, in terms of number of steps, I think that's actually more useful than thinking about it in space. Because right now, memory is dirt cheap. I can buy just about all the space I want. But putting together the time to do something, that's where it starts to make a difference. Right before this class, I was having a conversation at lunch. We were talking about using Gemini for some sort of coding relief. And the question was, well, if you switch from free mode to pro mode, does it slow down your computer? If I was doing all the work on my local computer, yes. But that's what all those data centers are for. That's where the work is being done. And it's just the internet speed between me and it. All that processing is happening somewhere else. I don't have to worry about this. To give you an idea of how crazy internet speed is right now, how many of you have had a virtual doctor's visit? I had a telehealth discussion with my doctor during COVID. And she asked me to get a particular piece of equipment that their local lab had. I wasn't to come to her office. I was to go to this medical facility and put my finger in an oximeter. It would measure my pulse and my blood oxygen. They wanted to know if I was breathing okay. That item sent the data immediately to my doctor as soon as I put it on. She had the information. I can do the same thing with the EKG. I want to know how your heart is doing. I put all the stickers all over your body and I measure your heart rate and I record all of that. In 1978, Westinghouse had a project to put this technology in jail. So you didn't actually have to have a doctor in the jail building. The doctor could be somewhere else, like the hospital down the road, and you had a patient in the jail. The guard could take him to the room, and the doctor would say, okay, I need you to put your hand in here so we measure your pulse and your respiration. I need you to lean over to this microphone so I can hear something. And you know how the fastest way to get information from the jail in Miami to Jackson Memorial Hospital in Miami, 22 miles away, was to buy a satellite. To get a dedicated satellite to relay that information. And right now I can do it over a phone, over a DSL line. We've got internet speeds that are absolutely light speed comparisons. So now time is, how long is this really going to take the computer to do? Talking to me is fast. So we do a lot of worst case analysis. What's the longest this algorithm could take? I have to remember if this says distinct values or just values. I'm going to give you a list of numbers. I want you to multiply each number by each other number and find the largest result. How many steps is this going to take? Well, let me actually give you the code because they gave it to me. Here's my code. How many steps will it take to run this code? There are a number of different ways to figure out what's going on. But I think the one that will work the best is to trace this algorithm, just like you did on the homework you just gave. Let's work our way through this. We start at the very beginning. We have m equals 0. The next line says I is going to start at 1. So I have one step. Then I is 1. Where does j start?
I plus 1.
Which means it starts right now at 2. And then I do this loop. And I go from 2 to 3 all the way up to n, right? And I do A1 times A2, A1 times A3, A1 times A4, A1 times A5. And each time I do a product, I say, hey, is this bigger than M or not? If the answer is yes, make it M. Throw away the old version of M. So there are a multiplication and a comparison in this line. This is 2 steps. A multiplication and a comparison. I've done that line n minus 1 times so far. Because what happens to I next? I finished this line. I jump out of this loop, which means I go back to this part, which means I now becomes 2. Where does j start?
3.
And goes to n, which means I'm going to do this line again this many times. How many times is this? Three, 4, 5, 6. The only ones I didn't do were 1 and 2, right? So I throw those out. But it keeps going. I would like you, for our next class, to have finished figuring out how many times we've done this J thing. Now, the reason I'm doing that is because I just hit the wall on time. Our next class isn't Wednesday. What's Wednesday? Founders Day. You saw it in the Founders Day talks. I will see you on Friday. Have a wonderful rest of your day.